In this section, we are going to view the tower column as a cantilevered beam of reinforced concrete. Currently, we do two checks for the tower column. For its flexural capacity, or bending, we check the capacity as a reinforced concrete beam using engineering judgment to determine that flexure will govern over shear in this case. Second, we will also check the cracking moment for serviceability concerns. A cracked tower column is not only concerning looking, but will allow moisture and water to infiltrate and further exacerbate cracking and corrosion of the reinforcing steel. So in some cases, the concrete column will be sufficient for strength, but it still might start to crack as it gets toward its limit, and we want to be checking that. First, we're going to calculate the flexural capacity, which will be similar to our anchor design lectures. For this, we'll turn to Chapter 22, Section 22.3 of ACI. In our concrete section, we will have a force couple formed by the compression in the concrete portion and the tension in the steel. This couple balances the flexural stress from the loading, and to find the capacity, we will find the limiting force that this couple can handle. In order to do this, we'll first find the depth of the concrete compression block. This is a rectangular approximation known as the Whitney stress block, with the depth A, calculated by A is equal to ASFY over 0.85 times F prime CB, where AS is the total area of steel, and for our tower, this is going to be two pieces at 0.31 square inches each for number 5 bar. Fy is the yield stress of steel rebar of 40 KSI, assuming we're using A36 steel. F prime C is the compressive strength of concrete, which is going to be, we're going to take as 10 megapascals, or approximately 1.5 KSI. And B, in our case, is the effective column section width of 40 centimeters, or 15 3/4 inches. You can see I plugged this all into our equation, and this gives us an A value of 1.23 inches. Another important dimension is D, our depth to reinforcing, which is the distance from the extreme compression fiber, or in this case the top of the section, to the centroid of the tension steel. We can take this as our D effective minus the concrete cover and minus the diameter of the stirrup or tie, and then minus half of the steel diameter. This shakes out to our effective concrete section of 70 centimeters or 27.5 inches minus 7.5 centimeters of cover minus the diameter of a number 3 stirrup, which is 10 millimeters or 0.4 inches, and minus the area of the number 5 bar, which is 16 millimeters divided by 2, minus half the diameter of the number 5 bar, which is 16 millimeters divided by 2, or 8 millimeters, 0.3 inches, giving us a D value of 23.8 inches. Do note this is all done for a standard tower section, so a standard tower detail, so you can go back and check this work if you want to derive it on your own, but if anything were to change with the tower section in the detail, you'd have to recalculate these values. Now that we have our A and our D values, we can get clever and take the sum of the moments about A over 2, or the centroid of the concrete compression reaction. I've shown that in green here on the force diagram. This gives us our nominal moment capacity, Mn, of ASFY times D minus A over 2, when we sum the moments. Now, to find our service loads, we return to the free body diagram from the beginning. And I'll take a pause here. The Mn value is our nominal capacity of the section. Now we'll have to compare this to our demand or to our loading. So to find our service loads, we return to this free body diagram. The overturning moment minus restorative moment, or the PH hand times the column height minus PV hand times the offset, where the column height is that 1.3 meter distance from the top of the tower to the bottom of the stage 2 concrete placement. It gives us our service moment. So it's going to be the resultant of what is trying to overturn the tower versus what is trying to restore the tower back to its original position. I forgot to add here as well that our service moment will have, or our restorative moment will also have our component of, its self-weight component. Now for allowable stress design, we would just compare our moment capacity to our service loads to find a safety factor greater than 1.5 or 1.5 mn over our factor of safety should be greater than or equal to our service loads or our demand. For LRFD, reinforced concrete design, we will be using LRFD. Here, we compare our design strength to our required strength, or our factored demand. Now, the required strength comes from the load factors multiplied by our service load effects. So from inspection, our governing load combination is going to be 1.2 times the dead load plus 1.6 times the live load. And converted into moments, 1.2 times our dead load moment and 1.6 times our live load moment. Once again, another reason to split your cable forces into dead load and live load contributions to be able to do these more advanced analyses. And make sure not to use the full load instead of the live load because you will be double counting here. So you'll have to go back through and find the dead load under just dead load sag, which will be the bridge self-weight, and the live load moment under the live load sag, but only the live load being applied. So we want to take that dead load out, so we don't double count when we're calculating that M live load service value I've written here. So now we'll go back and we'll find for LRFD our design moment capacity will simply be phi times mn, our nominal moment, where phi is 0.9 for a tension-controlled section. And if you remember from the anchor design lectures, we can confirm our section is tension-controlled with the following steps. So first, we'll take our ECU, which is the maximum allowable concrete strain. And by strain compatibility, we'll find C, our distance to the neutral axis, which is just our A value over beta 1, which is 0.85 for concrete less than or equal to 4,000 psi. You can take that value from ACI. Using similar triangles, which is where the strain compatibility comes in, we can calculate the strain in the steel, which is going to be strain in the steel over D minus C is equal to ECU over C. You can see how that equation comes from similar triangles in the diagram I've drawn here. And then our final step is to check that that strain in the steel is greater than or equal to its yield strain, which is going to be Fy, the yield stress, divided by Es, or in this case is going to be the elastic modulus of steel, which is 29,000 KSI. So specifically for 40 KSI bar, we have a yield strain of 0.0013. And we can then confirm it's tension controlled by calculating that EST is greater than that value, or confirming that this steel is going to yield. So we can go back and calculate our full design capacity of the section, which is going to be this equation that I've written out with all of our variables that we've calculated in the section above, and that will come out to approximately, for this section, 58.5 kilonewton meters. And ultimately, we'll go back and we'll compare our design capacity to our factored loading.